All right, we're going to go ahead and go through the free response section of the simple harmonic motion universal gravitation test. So the first free response problem is one of these cool lab ones. This is an older one though, so it's not quite the same as the lab format we have now. They don't ask quite the same questions, but it's similar sort of thing. So here it says, hey, there's a thin, flexible metal plate attached at one end to a platform, as shown, and it's used to measure mass. When free end of the plate is pulled down and let go, and you release, it vibrates, goes in simple harmonic motion with a period that depends on the mass attached to the plate. To calibrate the force constant, right? So that force constant, that flexible plate, right? Like the spring constant. Objects of known mass are attached to the plate, and the plate's vibrated, obtaining the data shown below. Fill in the blanks. They give us the mass that they put on and the time it takes to vibrate 10 times, to oscillate 10 times. And you're like, okay, well, the period, I'll just take that and divide by 10. So I move the decimal point over 1. Then it says, what's the period squared? So I punched in my calculator, boom, 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 5 numbers. There's my data. Now it says, on the graph below, plot t squared versus mass, and then draw in the line that's your estimate of the best straight line fit. So I plotted my data points and I dropped in a best fit line. I wasn't like super careful with this best fit line. Um, huh, I mean, reasonably well, I guess. Anyway, I went ahead and I did that. And I kind of like took my clear ruler and kind of said, well, I want to make it so I'm like minimizing the some of those distances that the data points are from a line. It's not a bad best fit line, I guess. Um, I did go just to like double check. I did this line and I estimated my endpoints here and like got like the equation for my best fit line just because I wanted to check and see how I was doing. So I kind of looked at the endpoints there and I even was like, I was pretty vague. I just said, hey, that looks like 3 1/4. Um, and say that this hit, let's just say that hit right at the origin. I don't know that it really should. It should probably hit above the origin a little. But anyway, um, and then say that's 0, and then this is 0.55. If I did that, then I would have this is my slope calculation: 3.25 minus 0. Saying that went through the origin, and then over uh, y final minus y initial plus x final x initial. So that would be 0.55 minus 0. And when you do that calculation, I got a slope of 5.91 for the slope, right? When I went and took this data, so this would give me an equation then, right? Using y equals mx plus b, right? So if I did that, this would give me an equation of my y variable is t squared. My slope came out to be 5.91. If I wanted to put units on that slope, sure, why not? It'd be rise over run, so it'd be in seconds squared over kilogram. Times, and my horizontal variable is mass, and then my intercept was 0. So like that's the equation that I came up with. When I went ahead and did a linear regression on this, so I just went ahead and plugged into Google Sheets the data points. When I did that, it gave me a line that was instead of like this, was just a little bit off like this. Um, yeah, so that it did have a little tiny intercept and a slope that was a little bit shallower, right? So, I was off by a little bit, but um, what they got for the equation line then was t squared is 5.73, uh, you know, second squared per kilogram times the mass, plus they had an intercept of 0.085 seconds squared. So you might say, hey, should this have an intercept? And you say, well, if the mass here, what is that the mass of exactly? If it's the mass I'm adding onto the plate, then if I had no mass on the plate and I go twang, the plate itself has some mass. It's gonna oscillate in some, real quick. So I should have a really a quick oscillation here. And I'm not getting 0 because I don't actually have 0 mass. There's the mass of the plate itself. So that's probably, well, the reason why we're getting a period here and an intercept that's not zero. Okay, so you get it, because the mass here isn't really zero, right? Really, like, well, you get it, you get it, you get it. Yeah. Okay, moving on. So the point is, this is the period when there's no mass on the added onto the plate. Anyway, I'm just going to go with the data I have. Fortunately, I didn't. They didn't ask questions about the intercept, so I didn't have to worry about the fact that my thing was off by a little bit. So I just used this value, a value that I had derived. And so when I did this, um, yeah, the question here is, okay, so now it says an object whose mass is not known is vibrated on the plate, and the average time for 10 vibrations is measured to be 16.1 seconds. Using this graph, find the mass of the object. So basically, what I do is I find the equation for my data, right, which you saw me do. I got my slope. I happened to choose intercept to zero here. That was whatever. And so when I have this equation, hey, they tell me the time for 10 cycles is 16.1. That means the period was 1.61, right? Seconds. So I could put 1.61 seconds into this equation for t and solve for what m is. So that's all you have to do. So this is going to be 1.61 squared is 5.91, or whatever slope you got when you did your best fit line, times m, and solve for m. With my slope, I got a mass of 0.439 kilograms. And you say, hey, 17.7 seconds vibration for for 0.5. That was like this data point. And a mass of 0.4 gave me this data point. So it kind of makes sense. 0.439. I'd have a period in between those two, and 16 points in between those two. So that makes sense. Um, Anyway, so again, you're going to get a value that's slightly off mine because I'm sure you're going to draw a best fit line with a slightly different slope than mine, and that is fine. That is fine. Okay, they have the AP scores when they score it. They have a range of values they can accept. Okay, moving on. Then they ask, explain how one could determine the force constant of the metal plate. Well, that force constant, that's like the spring constant, right? This thing's going to oscillate back and forth. It's got if it is a simple harmonic oscillator, which they tell you, simple harmonic motion, then we know the force that pushes it back to equilibrium is linear with respect to displacement. And so basically, this thing's going to act like a Hooke's law spring. And I know the equation for the period of a mass on a spring. Period is 2 pi root m over k. Again, on the AP formula sheet also. So we're trying to solve for this k. So I have this. And remember, we just got an equation that was t squared is, and I got like a 5 point, whatever the slope of your graph was, 5.37 or whatever I got. No, 5 point, I think I got 5.91. 5.73 is what linear regression was. But anyway, I got a 5.91. I'm going to use my value. Um, you know, times m. So this is, the idea is I've got a graph t squared versus m, and I got an equation for it that's t squared and m, and I need to get k. So t squared and m, and they're asking me about spring constant. So I really needed to find an equation that had all three. This is the one. I can turn this into this if I square both sides. T squared is 4 pi squared, and then the k would be in the bottom. And so look, this is the equation for my graph. This is the equation from the formula, from the physics. I can say, hey, look, my slope is equal to 4 pi squared over k. So the slope of the graph is equal to 4 pi squared over the spring constant. So I can find that spring constant, that force constant, by just taking 4 pi squared divided by my slope. Okay, so that's how I would do it. Okay, they don't actually ask me to calculate it. They just want me to explain. So I'm showing, hey, that the slope of the graph is equal to 4 pi squared over k, which I get from rearranging the period of a mass on a spring formula. Okay, E. Can this device be used to measure mass aboard the International Space Station as it orbits the Earth? You say, hey, if something is in orbit, then we talk about people appearing to be weightless and objects appearing to be weightless. And you're like, you can't just put them on a scale because they're not going to depress the scale at all. But this thing, it would still oscillate. You say if I take this thing and I put my mass on, attach my mass to it, and I go twang, it's going to oscillate back and forth. It doesn't need gravity to make it do that. So this thing would work just the same. Look, this G doesn't enter into the calculation at all. You're like, so yeah, this would work. So yes, um, I could attach the mass to the device and time its uh, period of oscillation. Then use the graph. Use the graph to find the mass that corresponds to the period squared, to the square of the period. Okay, but the point is, what they want you to say is, really is, um, hey, it'll work because uh, we don't need the gravitational force doesn't affect how this thing oscillates. It doesn't affect the period of oscillation. Um, so, okay. F. If the International Space Station is orbiting at 3.3 times 10 to the 6 meters above Earth's surface, what's the acceleration of Columbia? This should say the ISS, sorry. Originally, this was like referring to the space station, sorry, to the Space Shuttle Columbia, and I changed it to be International Space Station because that's what's orbiting up there nowadays. Anyway, what's the acceleration of the International Space Station due to Earth's gravity? They're giving me the radius of the Earth. We're this far above Earth's surface, so we're going to have to add this on to the radius of the Earth to find the radius of the orbit. So here's Earth, and we're orbiting up here, right? That extra bit above. This is not drawn to scale, obviously. I mean, to scale, look, times 10 to the 6 times 10 to the 6, 0.3 to 6.4. You're like, hey, look, that's just like a 20th of this distance above. Anyway, like I said, it's just above the atmosphere. Anyway, what's the acceleration due to Earth's gravity? You're going to say, well, again, trying to find acceleration. This is like the third time we've done this lab, this test rather. You're going to say, hey, gravitational force is, sigma F is ma. Hey, that acceleration when the only force is gravity is little g. We're trying to find little g. This is going to be big G, mass of Earth, mass of the satellite over the radius of the orbit. Now, the radius of the orbit, again, that's going to be the radius of the Earth plus that height above it, right? That I'm squaring m little g, and then those are going to cancel. So here we go. I can just plug in, they gave me numbers, I plug my numbers in. Big G is 6.67 times 10 to the negative 11. Mass of the Earth, they told me was 6 times 10 to the 24. Divide by, now my distance here is going to be 6.4 times 10 to the 6th plus 0.3 times 10 to the 6th, or 6.7 times 10 to the 6th. And don't forget, that's got to be squared. Is equal to G. So I punched that all in my calculator, doomby doomby doomby, and I got G to be 8.915 meters per second squared. Yeah, that's all good. Okay, and you say, hey, if I was at the surface of the Earth, it would be 9.8. I'm a little ways above, so it's slightly less. seems to make sense. Okay, part G. Since the answer to part F is not zero, the acceleration is not zero, why do objects aboard the orbiting International Space Station seem weightless? Again, you say, hey, the reason why they appear to be weightless is you say, well, in reality, as they are, here's the surface of the Earth, as they're moving along here, right, these objects actually have gravity pulling down on them. But so does the space station that they're in also has gravitation. So this has an acceleration inward of g, right? The g there, 8.915. But so does this. This also has an accelerate. They have identical accelerations, right? So if they both have the same size acceleration, then the acceleration is perpendicular to the velocity. So it's not going to make them get faster. It's just going to make them turn. They're falling all the time. There's no force up to balance this out. But the space station, International Space Station, is falling with an acceleration of 9.8, and the people inside are falling at 9.8. They're not, one's not falling faster than the other. They're not going to be running into each other, pressing against each other. They're just falling. It's like they're falling next to each other. They're not pressed together at all. So what I'm looking for here is that both the International Space Station and the objects aboard are falling with the same accelerations. Same acceleration. So they're not pressed together. And with no normal force means no apparent weight. Okay, so they feel like they're weightless. Okay, and that's that free response problem. Okay, free response number 2. This one, we've got a satellite of mass m in an elliptical orbit around the Earth, which has mass me for mass of Earth and radius of the Earth re. The orbit varies from closest approach of A. So at this point, the distance from the center of the Earth to the satellite here at A is little a is the distance. This point, by the way, that annoyingly they called A, this is the near point. So this is perigee, right? And then apogee is out here at B. It's annoying. I wish this had been A because then apogee A would go together, but whatever. What are you going to do? Anyway, anyway, they're at perigee here and apogee there. Anyway, when they're at, so this distance is A, and it says then they go to maximum distance B from the center at point B, right, at apogee there. Anyway, at point A here, the speed of the satellite is V. Now, you'd think they would call it VA, but they didn't. They call it V naught. And you're like, so at this point, I'm going, it's cruising like this with the speed V naught. Like, why do they call it V naught? Well, because we're going to do something in a later part of the problem to change the speed when it's there. So this is like the original speed before we make the change later in the problem. Anyway, assume that the gravitational potential energy UG is zero when masses are an infinite distance apart. You say, good, that's the way we like to do it. We've always done it. Express your answers in terms of A, B, M, mass Earth, radius the Earth, V naught, and big G. Okay, write the appropriate definite integral, including limits that can be evaluated to show that the potential energy of the satellite when it's at a distance r from the center of the Earth is given by this. In other words, show the integral that you would calculate with to figure out the potential energy equation. They're asking you to show the derivation of the potential energy equation is what they're doing. So what we would do, you say, well, I remember how to calculate a potential energy equation. The idea is I can look at the work done by the force that's associated with it and then flip the sign on the work to get the energy change. So we say, this is a general true statement that if I look at the work done by a force, in this case, the gravitational, and I flip the sign on it, then that'll give me, that's equal to the change in the potential energy that's associated with that force. Now we're going to cleverly, since we want to know the potential energy at r, when it's a distance r from the center of the Earth, I'm going to do a final minus initial here. Let's make it go to or from where the potential energy is 0. So the final or initial term will drop out, and I'll just have the energy for at r. So I went ahead and I did it. I just did a calculation from r to infinity. That's the way I set it up. So um, from r to infinity, yeah, then this is going to be final minus initial. So this would be the UG at infinity minus the UG at R, which is the thing I'm trying to find. The UG at infinity is 0, so this will give me the equation what I want with a negative sign. And then work by gravity, that would be the integral of the gravitational force dot dr. And I would do it from R equals R to R equals infinity, right? Where it says FG, I would put in, well, first of all, there's a negative sign there. I could cancel those. So I got the integral where it says FG. Well, let's just do one more step before I sub in there. Dot dr, well, the dot means I need to look at the angle between the gravitational force and the motion. I'm taking the satellite or whatever. Let's say if I was going to move it from R to infinity. So if here's Earth, I'm taking this thing from some distance R, some generic distance R away, out to infinity. If I move it out here to R equals infinity, as I'm going to the right, the gravitational force would be pulling against me. It would be doing negative work. So this dot is going to be a cosine of 180. So I'm going to get a negative 1 from a cosine 180 there. Okay. Good enough. So this negative canceled with this negative. So I just have UG there. This is going to kick. I'm going to go ahead and push this negative all the way out. But I should make sure that my answer ends up being negative here at the end. This negative is to show the direction. Anyway, hey, where it says FG, I can put in the gravitational formula now. Big G, mass of the Earth, mass of the satellite over that distance R squared, right? Times dr, going from R to infinity. So this is like the integral that I have to evaluate, right, to get my u function, but I'm just going to go ahead and do it out just to make sure I got everything right. Hey, constants kick out of the integral, so the g comes out, the me comes out, and the m comes out, and that negative 1 came out. So I've got minus g mass of the Earth mass, right? So I just have the integral now of 1 over r squared from r to infinity, right, dr. And you say, hey, the integral of 1 over r squared, this is r to the minus 2. The integral will be r to the minus 1, right? But if I took the derivative of r to the minus 1, it would kick a negative 1 out. So it's got to be minus 1 over r. I'm going to evaluate it from r to infinity. And I still have this minus g m out in front. So it'll be final minus initial. So I have a minus 1 over infinity minus a minus 1 over r. When I evaluate this this guy, I still have the minus g m in front. 1 over infinity, that's basically 0, right? Dividing by infinity. Minus minus makes it a plus. I still have that negative out front. So what I'm going to end up with is negative g mass of the Earth, mass of the satellite, right? And then this negative positive, this 1 over r. And that is what we were supposed to derive. So it seems to work. All right. So I think what they wanted to see really was this guy, I think is what they needed to see. Okay, moving on. Now they want to determine the total energy of the satellite when it's at A. And so you're going to say, well, the total energy of the satellite, I'm going to say the satellite's moving around, the satellite Earth system, their energy, this really should say of the satellite Earth system. It shouldn't just say satellite. Because they want to say energy is the kinetic plus the gravitational potential energy. My kinetic is going to be 1/2. Now, the thing that's moving here around, we're treating this like a stationary planet. It's just a satellite moving. Because it's such a small mass compared to the planet. 1/2 mass of the satellite. It's speed squared, 1/2 mv squared, right? But the v here is v naught, so it's a v naught squared. Gravitational potential energy is negative g mass of the Earth, mass of the satellite, over r, but the distance here is little a. So that's it. So that's my energy of the satellite when it's at a. Now I know what's the magnitude of the angular momentum when it's at a. Say angular momentum to the center, about the center of the Earth. So they're saying, hey, the center of the Earth, that's where the axis of rotation is. So that's there. And so you're going to say, well, I'm just going to use angular momentum. That's L is r cross p. So my r, that distance there, that's little a. P is m times the v. The v there is v naught. And then that cross product means there's a sine theta there. The angle between the momentum and the r vector. The r vector goes from the axis of rotation to where the momentum is, right? The momentum is this way, right? So we're going along. So it's a 90 degree. So it's a sine of 90. A sine of 90 is just 1. So it's just this. So my L is just AM V naught. That's my angular momentum at position A. Okay, now I want to find the velocity of the satellite as it possesses position B. You have your choice. You could do this with an energy calculation. We know that as this Earth satellite system, as it goes around, there's essentially no outside force acting on them, so there's nothing doing work. So I could say the total energy of the system here has got to equal the total energy of the system when I'm there. And so I already calculated the energy here. I could say that's equal to, this is equal to the 1/2 mv squared minus g MEM over b, right? Can I do that? Yeah, I'm allowed to use all those variables. Yeah, so I could do that and then rearrange and solve for v that way. Okay, but you know what? I'm going to do what I think is the easier way here. There's an even easier way, and that's to use conservation of angular momentum. Again, as this satellite's going around this point, the only outside force acting on the satellite is that gravitational, and that acts right along the r vector, so it's not causing any torque. Since it's not causing any torque, the angular momentum is conserved. So I can say that my L at position B has got to equal what the L at position A was. My L at B, that's going to be r cross p here, which is going to be, my r here is little b. The mass of the satellite's still m, because momentum p equals mv. And then the v at b that I'm trying to find. And then at b, I'm going like this. Again, my r vector is like this. Hey, that's a 90-degree angle, just like it was a 90-degree angle here. And so that's going to be a sine of 90, which is just 1. And the angular momentum at A we just calculated there, it's AM V naught. So to find VB, you're just going to say mass, move the B over. So my velocity at B is going to be a over little b V naught, okay, which was the velocity at A. Okay, like I said, you could just set the total energy. You can also do an energy balance if you want. This is, I think, easier. Okay, here we go, back page. Okay, now as the satellite passes point A, a rocket engine on the satellite's fired so that its orbit changes to become a circular orbit of radius little a. So it was whipping around here and then going way out there and then coming in, speeding up and whipping past here and going out here. Now we fire a rocket. Now it just goes around a little circle with that same radius there. Do you think it gained or lost energy to do this? Well, it's not able to fly out as far. It lost energy. It was getting here. We probably fired the rocket against it to slow it down. You know what I mean? To get it to go an orbit right around here. Anyway, but point is, they'd like to find the speed of it now that it's going circular motion here. So to find that speed, I'm going to have to use something special things I know about circular motion, and that's that whole relationship with centripetal acceleration. So I'm going to go ahead and use that idea that if I look at the sum of the forces in the radial axis, that got to be equal to mass times the centripetal acceleration. The only force in the radial axis is the gravitational force. That's the V I'm trying to find. And so I'm going to say, hey, that gravitational force, that's big G, mass of the Earth, mass of the satellite, over the radius here, which is little a squared, right? Mass of the satellite, v squared. The radius here is little a. Okay, try to find that v. Everyone says, hey, look, the mass of the satellite drops. This a will cancel the squared there, one of those a's, right? So that just takes square root. So I'm going to get that the root of g, mass of the Earth, over a is my v. Yeah, that's it. Okay, that's the speed. Now, can I tell? Not worth it. Okay. Anyway, now it says, can you find the work done by the rocket engine to make this happen? Like, well, I'm trying to find the work. Well, work is the change in energy, right? So it'd be like my change in kinetic plus my change in gravitational potential, right? Make sense? You say sigma, right? That's my big energy balance equation. However, what's happening is remember, I was going around in a elliptical orbit, and when I got to this point, we fired the rocket engines. Now, did I change my position? No, I fired the engine to change my speed. So actually, at this point, when I fired the rocket engines, I didn't change my height, so I didn't change the gravitational potential energy. There's no change in that. The work was done to change the kinetic, to slow it down. So work done is just equal to change in the kinetics. That's going to be my final kinetic minus my initial kinetic. My final kinetic is 1/2 m times my v squared. But look, this is my v, so v squared, I just take the radical off. Big G, mass of the Earth over a, right? So this is coming from here, right? Okay, minus the kinetic energy before. Well, before when I was here, they told me my speed was v naught. So that was a 1/2 m v naught squared. And so that's the work that was done. I guess there's a 1/2 m here and a 1/2 m here. You could factor it out if you wanted to. You might consider that this would be slightly prettier. I don't know. Question mark, question mark. I don't know. I don't know that you really need to isolate the 1/2 m like that. But anyway, that's it. Hey, that was the free response.